Okay, so this is the first session after your first test, and we're just gonna have a really short session because of that. I know y'all really wanna just go home and do whatever y'all wanna do, worry for other classes and stuff. But for chapter 5, we're just gonna talk about a really simple concept. It's called isomers, and with isomers, you need to know that they're pretty much two compounds, okay? And along with that, you know that they both have to have, yeah. Sure, yeah, okay. So you have isomers, and with isomers, you know that you're going to have the same of the two compounds, and with that, you know that both of them must have the same formula for those two types, okay? There's two kinds of them. The first is constitutional. We talked about this, I think the third session, but now this is really more important than before. And the second one is referred to as stereoisomers, okay? Basically, the difference between the two is that one is going to have different bond connectivity, but the same formula, okay? And I can give you an example of that. So, something like this. Okay. So this has the same formula, as you can see. There's 1, 2, 3 carbons in both of them, right? And there's also 1 chlorine. But the positioning or the arrangement or the bond connectivity of both of them are different. Okay? So that's an example of that. Also, you can look at another example like this. I'm going to erase this and put it back. So how many carbons are in both of these? How many? Yeah, there's 3, right? It's the points. But the thing that makes them different is that this is a single bonded ring, and then this one is a double bond made with another carbon coming off of it. Okay? So these are all examples of constitutional or structural. Just remember that they have the same formula, but they have a different bond connectivity. Okay? Next, we have stereoisomers. And with stereoisomers, you need to know that they have the same bond connectivity, but they have a different three-dimensional orientation, meaning the wedges and dashes are going to be completely different. Okay? So an example of that is that these two forms that I've referred to, I'm going to give with 2 examples. So the first one is going to be the first form, okay? Here's the first one. This one's going to be for cis and trans. Okay? So here's a good example. So both of these have 4 carbons in them, but the way that it's positioned within that compound is different. As you can see, both of these bonds are both going down off of the double bond, and then one is going down, one is going up. So this is an example of a stereoisomer. Okay?
If you go to the other side, you can turn this little knob and get in. Okay? Yeah, you're good now. I'm actually.
And this is the last example. Okay, so both of these are structurally the same. There's a cyclohexane ring with 2 substituents coming off of them. One of them, on the first one on the left, this one has X and Y both pointing out in the plane. It's pointing out of the board. And then with this one, it's the opposite from Y, but the X is the same. Okay? So I'm going to erase the examples. Now, having all of this in mind, this is what's going to help us incorporate another aspect into nomenclature, which I'm about to give you an example right here. Okay, so I don't know if y'all remember, but with Newman projections, how I kind of told y'all there was an eye coming out, and if you're looking at the projection, the wedge that's coming out is pointing out the board, and how I also explained the dashed H is the fourth priority, so it goes into the board. This is where priority comes into play, okay? So what's on the dash here? I mean the dash. So this is the wedge. So the one
hydrogen.
Exactly. It's implied to be an H. Okay? So what we're going to do is we're going to focus on this carbon right here and prioritize everything, which are the 4 bonds coming off that carbon, in the ordered priority. So if you had to guess which one would be the least priority out of these 4, coming off of this carbon. The hydrogen, right? Yeah. Okay, so that's 4. What would be the highest, you'd guess? The bromine, yes.
Yeah.
And the way you prioritize these is with its atomic weight, okay? And what would you say is the third?
CH2, CH3.
What is CH2, CH3 called?
That's
Ethyl, yeah. So then this whole group is referred to as 3, okay? No, sorry, 2. Yeah. And then this one is 3. Okay? Now the rule for this is whenever you're prioritizing your carbons like this, there's a reason for that. And that is because this carbon is referred to as a chiral carbon. Okay? Chiral basically means that the mirror image is non-superimposable, meaning that it doesn't have perfect symmetry in it. And it also means that since it doesn't have that perfect symmetry, the 4 bonds coming off of that carbon are all different. So as you note, this is different from everyone else. This hydrogen is different from everyone else. This ethyl is different from everyone else. And same as this methyl. Okay? So just, I'm going to write key terms regarding chiral. It's non-superimposable. Okay? Along with that, it is referred to as being optically active. And the last thing is you can just remember non-symmetric. Okay? So what is the name of this structure, the parent? So it's a form of butane, right? And where's my first substituent? It's on the second one. And what is it?
Bromo.
Yeah. And then how do I end it? Yeah. But what we need to know is the letter that goes corresponding to the 2. And what we do is you look at the structure and you go in order from 1 to 2 and you make a circle, okay? So 1, 2, 3, and then 4. So you have to go this way to get to 2 first, right? And then you look at what letter or which direction it's going. Since I'm going to the right, I have a steering wheel and I'm turning it to the right, that means this is a R configuration, okay? If I had a structure that was going the opposite way, then it would be referred to as an S structure. And whatever letter you have telling you the orientation, you write that next to the number in your nomenclature. So we know it was R, it's 2R bromobutane. That's how you do this, okay? Now, this is a side note that y'all should probably write down. If I had this same structure again, but the hydrogen was on a wedge, how would the priority be now? Would it be any different from the first one? No, right? So we know that the hydrogen's on the fourth, bromine's on the first, this one's on the second, this one's on the third. Now, when I make my round about going in the chronological order, how would it look like it would be? R or S? So if I make a complete circle, it's going to go like this. It looks like it's going to be R. But the important rule with priority is if your fourth priority, which is this hydrogen, is ever on a wedge, you have to flip it. Because the ideal situation for R in this configuration is for your lowest priority, which is the fourth priority, which is this hydrogen. If it's not on a dash, you want to flip it. So since we know this fourth priority, which is the hydrogen, is on the fourth priority, we take that R and we invert it. So then it changes to S. So the important thing is you want to first prioritize them and make sure that your fourth priority is on the dash. If it's not on the dash, then you flip that orientation, what it seems like it is. Okay? So are both of these considered chiral centers? The ones that have a star on them, are they both considered chiral? Or only one of them? They're both chiral. They're both chiral. Okay. So that's it for today. That's all I wanted to talk about. Actually, just one minor thing. That's it. One minor thing. So this is another way to show structures. You were shown cyclohexane chairs. You were also shown Newman projections. And this is the fourth. This is the third one. This is called Fischer Projection. Okay. So as you can see, it's like a T structure that has different groups going in different places. And what this is pretty much this. All the horizontal bonds going from right to left are always wedges, okay? And the bonds that are going up and down are always going to be referred to as dashes. So just write that down and put it in the back of your mind, and we're definitely going to go over this again next week in more detail. But the main thing I wanted to talk about were these different types of isomers, the basic ones, and how you can prioritize your groups and know what the configuration of the entire structure for that spot, which is this one, will be. So we'll go into more detail for isomers, determining what a specific type of isomer is. We talked a little bit about it two weeks ago, but we'll go more in depth next week. And then the same for this. Is there any questions before we finish for today?
What did you say about fraction?
This thing?
Yeah.
So basically the horizontal left to right bonds correspond to wedges, and the ones going up and down vertically, they're referred to as dashes. Okay. And you can put more than one horizontal line on this vertical line, but I just wanted to keep it simple for today. And that's it. That's it for today, guys.